Okay, so here I'm going to briefly talk about what a basis for a vector space is. Hopefully you now know the abstract definition of a vector space. I'm going to tell you what the basis of a vector space is. So the idea is it's a collection of vectors where you can add them and scale them to get any other element in your vector space. A very obvious example is consider, you know, the Cartesian plane r squared, or the vector space of r squared, the typical, I don't know what it's called, I should look that up. It's the typical vector space that you always think about when you think vectors. Okay, you can imagine if you have, say, this vector here, this is um 0, 1, and this vector here, which is 1, 0. If you want to get any other vector, say this vector here, and say this is -4, I don't know, and this is positive, let's just say 3. Then this vector here is just A is equal to, it's equal to 3 times 1, 0, plus 4 times 0, 1, right? Or if we want to label this, say, B1, and this is B2, then this is equal to 3B1 plus 4B2. Okay, so, and you can imagine adding these together like that, and 1, 2, 3, 4, like that. So this is the general idea of a basis. And now the idea as well is you want it to be the minimal possible basis. So for example, you could also imagine adding another vector to your basis, B3, but you don't ever need this vector, right? Because you can write this vector as a linear combination of these two vectors. So of course you don't need that vector. So it has to be the minimal possible um, set of vectors. So you can also imagine another basis, right? So you could have this vector and this vector. I imagine moving that over to the origin. I was just lazy. But you can create any vector from the combination of these two. So that's the idea of a basis. It's very obvious in the Cartesian plane in R squared, but it will become more useful when you're looking at more abstract vector spaces. So the the let's write out the definition, the more formal definition. So a basis B is a subset of your vector space, subset of V, such that, first of all, as we've already said, you need to be able to express any vector. So, right, for all vectors in your vector space, you must have it be a linear combination. Let me undo that. A linear combination, alpha 1, B1, plus alpha 2, B2, plus dot 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 dot, alpha n, Bn, must be a linear combination of of elements in your basis. So here, alpha 1 or alpha I are all real numbers, and Bi are all elements of your basis. So for example, up here, once again, your basis is these two vectors, and you can see A is 3b1 plus 4b2. So alpha 1 would be 3, alpha 2 would be 4. So that's the first thing. And then the second thing, as I was talking about, which is you want it to be the minimal such basis. And the way you enforce that is by ensuring that they are linearly independent. What that means is for any, subset of your basis, so let's say for any finite choice, so let's say B1 through dot 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 Bm of your basis elements, basis. Sorry, I should also mention here, this is actually can work for infinite dimensional vector spaces as well. Your basis does not need to be finite. So really this should be, as you know, you can do this up to infinity. But this one here is any finite collection of basis elements. You must have alpha 1, beta 1, arrows, plus dot 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 dot, plus up to alpha m beta m is equal to 0. That implies that alpha 1 equals alpha 2 equals dot 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 equals alpha m equals 0, right? So if you have some sort of linear combination of your basis elements, and that linear combination sums to 0, you must require that all of the coefficients be 0. And this enforces that you have a minimal such basis. I won't be proving that here. You can find some cool proofs online. But that's the idea of a basis of a vector space. So basically, it means that you can split any vector you want into some sort of linear combination of these basis elements, which we're going to find in future is going to become incredibly, incredibly important. So thank you for listening.